image. It's like looking at an image through a wine glass. And if you know what the image is that you're looking at, you can work out the shape of the wine glass. In this case, the shape of space and time. What measurements like this tell us is that there's much more matter in the universe than we can see shining in the stars and the galaxies. Much more, about 5 times as much. So the mass of this intervening galaxy cluster is significantly larger than you would estimate from looking at its luminosity alone. Now that matter, which it presumably is, goes by the name of dark matter. We strongly suspect that that's a form of particle other than the particles out of which we are made. And this is where cosmology interacts with my field, particle physics. The challenge from cosmologists and astronomers is we think there is evidence for a particle of matter that you have not yet discovered. Can you find it? Well, I think before we turned on the Large Hadron Collider at CERN, we thought that we would find it, and we thought we'd find it pretty soon. We had a series of theories which are built on, not invented, I should say, to explain the nature of this stuff the cosmologists tell us is there, but actually from more fundamental considerations in the theory of particle physics itself. We had theories that there should be a doubling of the number of particles we know of in the universe, theories called supersymmetric theories. And I think most of us strongly suspected we would see that and tie up the answer to this cosmological question, actually posed as far back as the 1930s by observations of the motion of galaxy clusters by astronomers such as Fritz Zwicky. Did we find it? Well, no, we didn't. We built the Large Hadron Collider. We found the Higgs particle, of course, another of the great holy grails of particle physics, which tells us, by the way, about events that happened close to the Big Bang. It tells us that not long after the Big Bang, as the universe expanded and cooled, something condensed out into empty space, something called the Higgs field. And what that does today is, by interacting with the particles of matter out of which we are made, it gives those particles mass. So it's a fundamental part of the origin of structure in the universe. We found that. That is no longer theoretical. It is correct. We found the Higgs particle. But we didn't find, or we haven't found to this date, supersymmetry.
Protons and neutrons are made of smaller things called quarks. And so we discover those. We've not discovered anything smaller than that, by the way.
Is it because you don't have enough energy to bust up a quark?
Yes. Or to resolve what's inside it, let's say, to build a microscope.
If we look as far as we can out into space, then we're looking back in time. You might be ready to participate in the record event, to go, the Stargazing World Record, to go and look out at the night sky and get the most people ever looking out into the night sky at the same time. You could also likely, I think, see the Andromeda Galaxy. Not quite sure about the time when it's going to be up, but look at the Andromeda Galaxy. You'll see light coming from it, which has travelled for 2 million years. So you're looking back in time 2 million years, because you're seeing the Andromeda Galaxy as it was 2 million years ago. We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang, actually. And in that light, before there were stars and galaxies, there are also patterns, which are patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is a theory called inflation, which says that before the Big Bang, in the sense that before the universe was very hot and very dense, it was still there, and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. So that's called inflation. And many physicists think, so there's good evidence for that. Now many physicists think that that inflation doesn't all stop at once, but stops in little patches. And so you have a little patch of this rapidly expanding universe that slows down and makes a Big Bang, and that would be our universe.
and then the rest of it carries on, another little patch slows down and stops, and you get another Big Bang, and that would be a different universe. Another bit stops, and you get a Big Bang and a different universe, and so on. So that's called the inflationary multiverse, which is what was in your question, a multiverse, a load of bubble universes, if you like, essentially an infinite number. And that could be our reality. It really could be that our entire universe, which is much bigger than the universe we can see, with 2 trillion galaxies in it, is one bubble in a multiverse of bubble universes. And is there any evidence for that? There's evidence for the inflation bit, which slows down and stops. There's no evidence for the other bubble bits. So could we ever see evidence? People speculate that you could perhaps, in the most ancient light in the universe, see a pattern that suggested that maybe there was a nearby bubble that formed at the same time, but we haven't seen it yet. Or it could be that the theory becomes so well developed and it describes things so well that we see in our universe that you start to think, well, the theory is suggesting that this is the only way things could be.
So Saturn, Jupiter, you'll see the cloud tops of Jupiter. You will also see the Galilean satellites, these 4 moons that Galileo discovered in 1610, which were central actually to the development of our modern civilization, because they were one of the key pieces of evidence that told us that everything doesn't go around the Earth. Galileo said this, it's obvious they're going around that planet. So you can sit there and watch them. And actually Io, the innermost one, you could pretty much see move over the course of an evening if you catch it in the right place, because it goes around so quickly. Then you have this observation with your own eyes that was of immense historical importance. So yeah, the planets, but then you can start, if you've got darker sky, even a small telescope or binoculars. Actually, you'll see the Andromeda galaxy. That really, to see that, it depends. It's not really the telescope again or the binoculars. It's just the darkness of the sky, and you'll see Andromeda, and you can say that I think is quite big on the sky. It's dim, this misty patch, but it's big, and it's over 2 million light years away. So I say to people sometimes, think about that. It means the light that's entering your eye now began its journey long before we had evolved.
Protons have a charge so that you can put them in a magnetic field and accelerate them to very high speeds.
Yeah, so they go around. So the LHC in kilometers is 27 kilometers, and that's the number I was at.
Circumference.
Yes, that's about 16 miles or something like that.
Mm-hmm.
And the protons go around that ring 11,000 times a second. So that's how fast they go.
That's fast.
So that's 99.999999% the speed of light.
Okay, so you've granted them energy so that when you collide them, you break them apart. You're basically deconstructing nature to see what residue comes out of it. When I think of doing that for anything else, it's going to break. Right? I don't take chairs and slam them together and still have chairs. I have a pile of kindling. Okay. So who ever thought it was a good idea to smash nature into itself?
Well, I suppose Ernest Rutherford initially. So we go back to Manchester, the turn of the 20th century, and Rutherford was using radioactive decay. To essentially produce the particles. I mean, it's just the decay of atomic nuclei that naturally happens to produce high energy particles, which he then fired into gold foil and bounced them off the foil. In doing that, he discovered the atomic nucleus. So one way to think about particle physics is that when you collide things together, what are you doing? You're really building a microscope. One way to think of it is that the higher the energy of the collision, the faster these things are traveling, the smaller the object you can see. So we were talking about seeing for the first time
in those experiments the atomic nucleus of the frequency or the wavelength of light emitted from hot objects. Photons, what's the energy of a photon, a packet of light? It's Planck's constant multiplied by the frequency. So it's a deep property of nature. Those three numbers, those three things, the speed of light, strength of gravity, and Planck's constant, allow you to define some distances, a particular distance called the Planck length. I want to do it by reading it off something, because I don't carry all these numbers around in my head. It would be pointless to do that, because you can look them up. So I could take Planck's constant, multiply it by the strength of gravity, and divide it by the cube of the speed of light, and then take the square root of the whole thing. So it's hg divided by c cubed square root. You'll find that has, if you put those things in terms of meters and kilograms and things, you'll find that it's a length, has the dimensions of meters, and it's a tiny length. It's about 10 to the minus 35 meters. 0.00000, 35 noughts, 1 of a meter. But that is a length that we've calculated by measuring the strength of gravity, the speed of light, and Planck's constant. So it would seem that it should have something to do with the deep structure of the universe. And indeed, it does. How important is it? Well, let me give you some examples of the Planck length. So it turns out that if you ask a question, how much information in bits is stored inside a black hole? Right? That would seem to have nothing. What's that got to do with all this? Right? How much? It turns out, in a calculation that was done by Jacob Bekenstein in the 1970s, it turns out that the entropy of a black hole, which is the amount of information hidden within it, is equal to the surface area of the event horizon of the black hole in square Planck lengths. That's an astonishing result. But just think about that for a moment. It's telling us that the amount of information stored in a region of space, in this case a black hole, is equal to the surface area surrounding that region in square Planck lengths. That's a bizarre result. So it does seem that the Planck length is fundamentally important. And here's another property of the Planck length. So let's say we want to make an observation of some very small thing. So how do you observe something that's very small? Well, one way to do it is shine a light on it to see where it is, right? Together, that's the way that we observe things with our eyes.
Oh, I mean, the first most stunning thing, the easiest thing with the telescope, even in a city, is to look at the planets. Any telescope will show you the rings of Saturn. And obviously, the more powerful or the darker the sky, the better the atmosphere, the more detail you can see in the rings. I have a telescope myself, a small telescope, and I can see the Cassini division, which was first seen by Cassini, of course, back in the division in the rings. So you see more detail. That Saturn is, I think, pretty much everyone that I have shown that to. So everyone who's looked through the telescope I have and seen Saturn for the first time becomes emotional about it, because it looks like a child's drawing of a planet. And it's impossible. So you go from the telescope, you look through the eyepiece, and then you look at this little point of light, this little yellowy point in the sky with your eyes, and then you go back to the eyepiece and you go, it can't be this.
We'll be sending humans to Mars, certainly in your lifetime. And one of the things you'll be doing is looking for microbes below the surface. So maybe we'll find Martians. But if you mean aliens in spaceships, that means civilizations. We don't know. We've looked a bit, we've listened for radio signals from other stars, we've found nothing. We have no evidence of alien civilizations at all. That might mean we haven't looked hard enough because we haven't looked particularly hard. The galaxy is very big. But it might also mean that civilizations are rare. And the one thing I would say is that if you speak to biologists, they will be more pessimistic about discovering civilizations than astronomers, I think. Astronomers tend to say, don't they, there's loads of planets, loads of planets, there must be some. But biologists say, well, but if you look at life on Earth, it began, we have good evidence, it was on the planet, let's say 3.8 billion years ago. So let's say it may have begun even 4 billion years ago, after the planet settled down and the oceans first formed. It took 4 billion years, let's say, to go from the origin of life to a civilization, which is about a third of the age of the universe.